A very good afternoon to everyone. I take the privilege to introduce our today's expert, Dr. Rajiv sir. Sir is currently working as professor in mechanical department, Amritha Vishwa Vidyapeetham. Dr. Rajiv completed his BTech in mechanical engineering from NIT Allahabad in 2006. He did his MS in mechanical engineering from IIT Delhi in 2009. He was awarded PhD from the Department of Mechanical Engineering, IIT Delhi in 2023. He is serving Amritha Vishwa Vidyapeetham, where he is enjoying his teaching and research. He has published more than 50 papers in international journals and conferences. At IIT Delhi, he was the co-developer of software for effective teaching and learning of various concepts of engineering such as RoboAnalyzer and MechAnalyzer. He has been invited to more than 40 technical talks or sessions at various reputed institutes. Dr. Rajiv serves as Association for Machines and Mechanics as its secretary and the Robotics Society as its student activity coordinator. His thrust area of expertise are robotics, railway dynamics, multi-body dynamics, CAD simulations, mechanics, and computational engineering. So we are very fortunate to have you here with us for today. Please proceed with the session, sir. Sir?
Thank you, ma'am, for your kind introduction. Thank you, sir, for inviting me over to this FDP. Let me share my screen. Okay, just something that happened. I had gone to cast my vote. I just returned home. So I'm very fresh after voting. So this is for your kind information. Okay, so this session, sorry, sir.
Congratulations, sir.
Oh, thank you. Thank you. So let me just have a quick look at how many people are online. There are 28 more coming in. So let me just wait for a couple of minutes because usually first 2-3 minutes people keep turning up. We'll just wait. Okay, so this will be a kind of a hybrid session where we'll have some form of interaction. So the interaction, I mean, we'll start with some introduction. Then there will be 1 or 2 small, let's say, quiz. I'll be sending Google form link where you will have to fill up something and we'll get some idea how interactive you are. Okay. And just to give you some idea, let me show you a folder which has all the sessions that I have conducted so far. So it's been, let's say my first session was in 2016 and all the way to today's session that is in Vasireddy Venkatadri Institute of Technology. Okay, so just a count of it, you can see that it is almost 53. So more than 50 sessions have happened like this. So obviously there'll be a lot of learning from both the sides. I'll be trying to share whatever I know, and obviously I'll also be looking at your response in between. Okay. So having said that, let me just see. Yeah, we have 35. Shall we start, sir, or do we expect more people to join?
Yes, sir. They will join, sir. You may continue, sir.
Okay, fine. Thank you. Okay, is my screen visible?
Yes, sir.
Okay, so I'll not go to full screen mode because I'll have to keep using the tabs. So the topic of my session today is robot kinematics using RoboAnalyzer. So So RoboAnalyzer is a software I co-developed at IIT Delhi. That is what is mentioned here. And currently I'm a faculty in Amritha Vishwa Vidyapeetham in Bangalore. So these are some of the screenshots of our software and some of which I'll be demonstrating towards the end of this session. Okay, so I suppose the crowd or the audience is from different aspects of engineering. So some of these are specific to mechanical, but otherwise, let's say robotics is interdisciplinary. So obviously, whatever simple mathematics that we'll be covering, it is applicable to many fields, including computer graphics and let's say CAD. Okay, some of the contents that we'll be covering. Okay, so for those who belong to mechanical or otherwise, is just that when we go to robots, we have to study certain topics. Okay, so this is also the way the curriculum of engineering, especially mechanical engineering, is there. So we deal with subjects such as engineering drawing, engineering mechanics, which was also sometimes common to other branches. Then specifically, we deal with machine drawing, kinematics of mechanisms, and also we have to learn programming. Or if you don't know programming, then I mean, it is very difficult to survive in this engineering market. So once all this is covered, then we deal with other subjects such as strength of materials and dynamics of machines. Okay, so the complexity keeps increasing. And finally, we deal with something known as design of machine elements, where the exact shape and material are selected, and also stress analysis and other things that are covered. Okay, so these become precursor or prerequisite courses to deal with robotics course. Okay, because robotics only comes after all these courses. Okay, some of you already have heard of this word mechatronics. Mechatronics is a combination of mechanical, electronics, or electrical and computer science. Typically, the mechatronics are not multi-purpose. That means you have a system that works only for one particular application. So for example, the application that is mentioned here, FASTag, toll gate that opens. So when a vehicle comes, there's a FASTag RFID sticker, a sensor senses it, then it computes, and then gate opens. So as you can see, it has all kind of interdisciplinary nature, and it is a perfect example of a mechatronics. Then robotics, I would say it's part of mechatronics, and also it is slightly different. How is it different? Let me see. Robotics is a field related to a robot. Okay, what is a robot? That will come next. So robotics deals with study of mathematical model where input and output characteristics are understood. Then we deal with the design of a robot where different dimensions components are chosen. Then we develop physical prototype and virtual prototype. So this physical prototype and virtual prototype is very important when you actually make a robot, right? Then we have to apply it for some good cause. Okay, what is a robot? It is a device or an equipment. And these are some of the keywords that you should know. Robots, it repeats instruction. It can be taught. So, and it is adaptive in nature. That means you can reprogram and make it multi-purpose. Then it is also smart because it has some sensors and it can also take some automatic or autonomous decision. And finally, robot has to follow certain laws. So the summary of the laws is it should not hurt humans, nor it should hurt itself. Okay, so this is what is very briefly what is robotics. Okay, now I would like to just give some insights on what is a robot and what it is not. So for example, this particular small device, what you see, there are two wheels, motors, then there is some circuit and buttons. So depending on what buttons you press, this can go front and back. Okay, it will rotate, turn, make a turn. Okay, so what does it mean? It means it can operate, but it is a fixed automation. That means there is no sensor here or there is no intelligence here. So this is more like a toy, or let me say mechatronics. Okay. However, if you have a system like this, which has sensors and which has programming and which has some input output setup, So which can take its own decision. So that becomes a robot. That means it can do multi-purpose. You can use it for different applications. Okay, so this is the simple definition or division of what is a toy and what is a robot. Many of the schools, they start saying that this is a robot, right? This is definitely not a robot. It is definitely the simplest form of, let's say, a robot, but obviously we can't be happy with this as a robot. Okay. Now, another confusing set of words is automation and robotics. What is automation? So let's say, for example, I want to move a block from one place to another. So this particular mechanism, it just has one motor and it is able to move certain blocks. So this is an example of automation. So that means something is moving automatically and it just does one application. However, a robot is something like this, what you see. You have a sensor, you can identify different component that there is a robot or a manipulator. It is basically segregating some objects. Okay, so this is an example of automation and robots. Okay, so now let me just stop sharing my screen and I'll give a simple quiz to see how many people are actually present. And you should be able to make it more, I would say, interactive. Okay, give me 1 minute. I'm just getting one Google form. I'll be pasting in Teams. I request all the participants to open this and just participate. Sir, can someone tell me whether they are able to see the chat?
Yes, sir, it is there, sir. Form is
Okay,
there.
so yeah, kindly open that. Even the organizers, it's a simple question. Let me start sharing screen. Okay, this is what is the question. You have to mention one verb. Verb is an action word. Okay, I go to school. Go is the word. I eat my lunch. Eat is the verb. So like that, give any one verb which you think you can relate to a robot. So this sets the stage, like what you understand and how much deep I have to go. So please fill this up. You have 2 minutes. Okay, so I'll be looking at the responses. Actually, we'll all be looking at the responses. So 2 people have submitted, 3. See, as I said, this is going to be an interactive session, so kindly participate. Five people have participated so far. You have to give one verb, whatever you think. Another 1 minute, please. If there's any WhatsApp group for the participants, organizers may kindly put it there so that they come back and
Shall I post this link, sir?
yes, please, so that they know that something is happening. Maybe
Yes. Yes.
we both understand why that is required. Okay, 9 people have responded so far. Okay, another 30 seconds and then we'll stop accepting the responses.
So just
So
now I
this exercise.
posted this link.
Okay, sir. Thank you.
Yeah.
So this exercise basically is, one is to see how many are actually present. Second is also to get some idea of your, let's say, understanding of robotics, what a robot can do. Okay, another 15 seconds, then we'll stop accepting the responses. So courtesy COVID, we were able to come up with all these strategies to have online classes effective. So in between classes, I would just make up a quiz and send it to them. And that was probably one of the reason the students, after we reopened, they came back and said, so it was a good strategy. It kept us listening. So it's just one small tip for the teachers. If we want, because the organizers have put in a lot of efforts, resource persons, it is just a couple of hours, not much, right? You people have been attending all these sessions. Obviously, we have to justify the efforts and finances associated with such FDP. Okay, I think we'll just stop accepting the responses. Yeah, let us just review what are the answers given by you people. Okay, so there are answers like this: automatic forward and reverse, lift, specified action, work, amazing, move, walk, run, forward, work, make automatic, specified action, move. Now what you can see is jump, lift. So this particular word move seems to be having maximum frequency. Let's say 3 plus 1. 4 people have marked as move. So lift, run, jump all require some form of motion. Okay. So if something that does not move, then it does not become a robot. So the most important verb in my opinion is motion, move. Okay. So now we'll start looking at certain aspects of motion. Okay. So to deal with motion, we have a subject or topic named transformations. So this is what we'll be learning now. Okay, so I'm going to use my, since it's a holiday, I don't have my digitizer, but anyway, we'll start with this. Okay, so we have a word or a definition of degrees of freedom. Okay, so let me just try to ask you certain things. Again, please pardon me. I am not having my digitizer, so I'll just try to use it with my mouse. Okay, so there is a point P in a two-dimensional system, XY coordinate system. Now, if I want you to draw this particular point P in that system, what information should I give you? Let's say you have a graph sheet and you want to locate a particular point P. Can you please type in the chat what information would you be requiring from me? Please type in the chat what information is required to locate or draw a point on a 2D graph sheet. So that is the question. Coordinates. Okay, Suresh sir, can you be specific? What exactly do you mean by coordinates? Okay, Ms. Deepika, X and Y coordinates. Perfect. So if we know X and Y coordinates of this particular point, so that means we will be able to locate that point. So this is Px. Similarly, this is Py, the other one. See, all information what we learned today is already known to you. It's just that we'll be packaging it in a different manner. Okay. So Px and Py is there. So that means what is degree of freedom? Degree of freedom is number of independent parameters or variables required to represent a system. Okay, so this is what is degree of freedom. It's a number. So degree of freedom is number of independent parameters. So let me just bold this independent, underline this, because that is what is important. What is independent? That means it is not dependent on anything else. I can choose any random value of Px, any random value of Py. Okay. So what is the degree of freedom of this particular point? What is the degree of freedom of a point in 2D space? Can you please type in the answer chat? Okay, X and Y coordinate number, I want a number. Suresh sir says 2, Janardhan says, sir says 3. Anyone else? Two. Bhavani ma'am says 2. So it's a number. Degree of freedom is a number. So that means we need two parameters, px and py, to represent a particular point. Okay. Now let me just try to use a different scenario. The same point P can we represent using polar coordinates? Yes, we all have studied this. Okay, so where we have a particular point P represented using r and theta. Okay, so here also, as you can see, if I just give you the value of r and theta, you will be able to locate point P. So that means degree of freedom of that point is still 2. Now, can we do something else? Can we have a point with px is equal to 2, py is equal to 2, r is equal to 2, and theta is equal to 45 degree? Is it possible? Please type in. Can we have a point with these coordinates? Px is 2, py equal to 2, r equal to 2, and theta equal to 45 degrees. Any point in 2D, can we have this condition, or is it possible? Please say yes and no. No. Suresh sir says no. Janardhan sir says no. Rupa ma'am, Bhavani ma'am say yes. Okay, I need more answers. Amartej sir says yes. Please think. Class 11th and 12th students will not agree to this statement. You should see, now I see there is a trend. So earlier people saw the question, later people are just seeing what is above and then they're typing. Now this is bad. We are all teachers here, so please respect. Can we have a point with px is equal to 2, py is equal to 2, and r equal to 2, and theta equal to 45? No, it is not possible. Why? Geometrically, that doesn't make any sense. This is px. Oh, sorry, this is py. This is px. If this side is 2, this is 2. R square is equal to px square plus py square. It's a right angle triangle. So this r value has to be root 2. It can't be 2. Okay. Let's see what people have said. Correct. So square root of 2. Yes, Suresh sir. That is possible. So what I meant to say was, out of these 4 values, r, theta, px, and py, only 2 can be independent and remaining 2 have to be dependent. Now, how are they related? Let me just type it here. So we have something known as if px and py are given, then you can write r square is equal to px square plus py square. Okay, so this we know. Another thing is tan theta is equal to py upon px. So if the value of px and py are given to you, the other two value r square, r is equal to square root of px square plus py square. Theta is tan inverse of py upon px. So this is what we have. Okay. Now these two equations, what we just derived, are known as constraint equations. So that means they are constrained. R and theta are constrained to have these values. They can't have random values. Okay. So this is not possible. This has to be square root of 2. Then only it is possible. Okay. Now, what if is it possible to have the other way around? So that means if I give you the value of r and theta. Okay. Can you please type what will be the expression for px and py? Px is equal to something, py is equal to something, right? So please type what you mean by that. See, r and theta are given. Let's say r is equal to square root 2, theta is equal to 45 degrees. Can you find out the value of px and py? You should be able to do looking at this diagram. Let me give you a hint. Trigonometry. R and theta are given. So you have to find the value of px and py. Basic trigonometry. Can you please type the equations? Okay, Janardhan sir has given one equation. Yes, please. Can you please type like what Dr. Janardhan has given? Okay, so he has given both the answers. So let me type it here. Px is r into cos of theta. Py is r into sine of theta. Okay, so it's trigonometry. Cos theta is equal to adjacent upon hypotenuse. Sine theta is equal to opposite upon hypotenuse. The same thing has been written in a slightly different manner. Okay, now this particular thing, what I mentioned here, it's the most fundamental things that we use in robotics. Px is equal to r cos theta, py is equal to r sin theta. That is something that we are going to keep using again and again in the next couple of hours and also in the field of robot. However, there is a small, there is a precaution that we have to take. What is that precaution? Theta is always measured counterclockwise from positive x-axis. So if you are writing down notes, please make sure that you write this down because this is the single most important thing in engineering mechanics, single most important thing in robotics. If we make a mistake here, then everything else goes for a toss. Okay, so as we go along, we'll see why this is so important. Okay, so let us do some simple stuff. So let me just try to duplicate it. Okay, we'll continue with degrees of freedom. I'm going to keep drawing new systems and you'll have to keep writing the answers. So there is a point P1 and there's a point P2. What is the degree of freedom of this system? Can you please type? So this is where the fun begins. Okay, so far it was just elementary stuff. Now we'll start looking at important stuff. So there are 2 points P1 and P2. What is the degree of freedom of this system? Please type. Two, 4. Janardhan sir, what is your answer? 2. There are 2 points. Please remember the definition of degree of freedom. Degree of freedom is how many independent parameters should I give you so that you can draw the diagram. Bhavani ma'am 4. Deepika ma'am 4. How about others? It's a simple system. We haven't even reached robots. Okay, the explanation is correct. X1, Y1, X2, Y2, or P1X, P1Y, P2X, P2Y. So we require 4 parameters and hence degree of freedom of this is 4. Okay. Now let us try to do something else. So I'm drawing P1 and I'm drawing P2. And I decided to connect them using a spring. Okay. Now, what is the degree of freedom of this system? There's a point P1, there's another point P2, and there's a spring that is connected between these 2 points. Please mention the degree of freedom of the system. Okay, Bhavani ma'am says 4, Deepika ma'am says 4. Sorry, Bhavani ma'am says 5. Deepika ma'am says 4. How about others? See, we'll reach robots in next 5 minutes. So please bear with me. Number of turns. That's interesting. Number of turns. It's not important because we just have to know what is the state of the system. Number of turns, radius of the spring, length of the spring. So many factors are there. So what all are required? 4. Okay, let me try to give it this way. When I drew the system, I drew P1 and P2. So this is exactly same as above. So I just require 4 parameters to draw 2 points. Once the parameters are fixed, then only I used a spring to connect. So that means if the length of the spring is L and if this angle is theta, okay, so L and theta are known once you fix the values of P1 and P2. So these 2 are more like dependent parameters. Okay, they're not independent. So therefore, the degree of freedom of this system is also 4. Okay, any doubts? You may please type. I know this is where most of the times people have confusion. You can also look at it this way. I can have degree of freedom or independent variables as P1x, P1y, L and theta. So this is another scenario. If I know the value of P1 and L and theta, I should be able to go to P2. You remember from the previous slide, this becomes L cos theta, L sin theta, this particular distance. This is going to be L cos theta. This is going to be L sin theta. OK, P2x is going to be P1x plus L cos theta. P2y is going to be P1y plus L sin theta. OK, so depending on what you take as independent and dependent, there is a slight variation in the way the formulations are made. OK, so this is what is degree of freedom of a particular point. Now let us understand something known as rigid body. A rigid body, let me give you a definition. A body that does not undergo any deformation or shape change when an external or internal force is acted on it. OK, so that is the definition of a rigid body. That means a body that does not undergo any deformation. Right. So typically in our practical purposes, say mobile cover usually is flexible. So that means if I bend it, it gets bent. However, this, let's say mobile is kind of sturdy. It is not changing shape even if I apply some force. Some minimal change is there, but we can ignore that. OK, so rigid body is very important assumption in mechanics and also in robots. So that means we assume that nothing changes their shape. There is a different topic called as soft robotics where you have shape changing actuators, right? So that is a different story. We'll not be dealing with them. OK, now rigid body. Let me just give you an example of a rigid body. Most of us are, let's say, teachers, right? So we use something known as a duster on a blackboard, right? So duster, we can assume it as a rigid body. OK, so let me try to get some inputs on this rigid body now. So if I have a duster like this, OK, imagine this is a duster and I want that duster to be on the blackboard. OK, so this is the duster. It is on a blackboard. Now the question is, in how many directions or in how many ways can we move this duster? OK, let me just try to readjust my screen. In how many ways or directions can we move a duster on a blackboard? So that is the question. In how many ways can we move it? How many ways? I would say, OK, can I translate like this such that the duster is still on the board? Can I translate like this? This is another motion. OK, what is the third motion? I can rotate like this such that the duster is still on the board. I can just rotate the duster. So there are 3 independent motions. OK, so that is what we are going to deal with. Okay, I get some. So this particular thing I can translate like this. I'll call it as translation in the X direction. Then I can translate like this in the Y direction. And I can also rotate it. Okay, now this rotation, so if X and Y is here, so the Z axis is coming out of the plane, out of the board, right? So this rotation is nothing but rotation about Z axis. So that means we have a new definition of degrees of freedom, that is number of independent motions possible in a system. This is another definition of degree of freedom. So that means how many motions are possible. See, Tx and Ty, though they are in opposite, we will consider them as one motion because it's just change of sign. One side is positive, another side is negative. Similar Ty, similarly R. So that's why one of the teachers mentioned 6. So 6 is not the correct answer. 3 is the correct answer. Okay, 3 independent motions are possible. Now this is for a rigid body, one rigid body, right? Now let us look at slightly different versions now. Now this is where it becomes related to a robot. Okay, I have 2 rigid bodies. Okay, 2 rigid bodies. What is the degree of freedom of this system? Please type. Two rigid bodies in a 2-dimensional system. What is the degree of freedom of this? Okay, Janardhan sir says 6, Deepika ma'am says 3. So we'll also be having another quiz in a while based on these questions. Bhavani ma'am says 3. Okay, let me give you a hint. These two bodies are not connected. They're just there. It's like two dusters. I can move this duster. I can move this duster independently. What is the answer? Independent. That is very important. See, this guy, I can translate it. This also I can translate. And I can rotate it. Okay. Similarly, this also I can translate in 2 direction and I can rotate in Z direction. So total degree of freedom of this system is 6. 3 for the first body, 3 for the second body. Okay, I think now people are getting it. I think Anwar sir or whoever is there, there are a lot of people who are trying to join. Kindly keep admitting. Sometimes it's still there.
No, sir. Always we are admitting.
Oh,
whenever
okay.
they are joining.
Yeah, there's some delay. No problem. Okay, so now we have another system. Please pay attention. There are two rigid bodies, and I have connected the two rigid bodies using something known as a hinge. Okay, hinge or revolute joint. Like a door hinge, or we also call it as revolute joint. Revolute joint means it allows, let's say, rotation. Okay, so there are two bodies. What is the degree of freedom of this system? Please type. So this is body number 1. This is body number 2. What is the degree of freedom of this system? Okay, others are not answering. There are two bodies. The body number 1 is also free to move. I'm not fixed it. Anti-clockwise, clockwise are actually same. One side is positive, one side is negative. So there's a trick in this question. What is the trick? I've not fixed any body. So that means the first body will have 3 motions. Okay, so that means I can move the first body. It is not fixed. But the second body cannot have 3 motions because it is having some constraint. So that means I can only have a relative rotation possible between body 1 and 2. Right? So that means this is Ford off. The first body will require 3 degrees of freedom. The second body will just require 1 rotation. So that rotation is, please remember, it is an independent motion. I can move it, I can lock it, I can do whatever I want. So hence degree of freedom of this system is 4. Okay. Now let us look at a system which is like this. So this symbol is basically used in mechanics and other places for fixing. So I fixed one of the bodies and I've connected another body using the same hinge. It looks like some dog. Okay. So there is a link that has been fixed. So when we fix something, it does not have any motion. And there is another link which is fixed to the first link and it has a revolute joint. Now please type what is the degree of freedom of the system. Okay, now I think people are understanding. Yes, the Janardhan sir and Deepika ma'am, degree of freedom is correct. Now there is only one relative rotation possible. Okay, so that means degree of freedom of the system is 1. Only one motion is possible. Okay, some more examples and then we'll go for next topic. Okay, now we have looked at a system. Now let me try to make another system. Please pardon me my drawing. I'm using my laptop pad. Okay, so these are the bodies, and wherever I'm drawing small black circles, they are our revolute joint or hinges, which allow relative rotation. Okay, can you please type the degree of freedom of the system? Please understand the drawing is very important. You should focus on the drawing and then you should come up with your answer. What is the degree of freedom of this system? It's look like a human. Chest, torso, neck, arm, forearm. Okay, what is the degree of freedom of this system? Okay, Janardhan sir says 8, Deepika ma'am says 4, Vasanta Lakshmi ma'am says 3. She updated to 5. Others? Okay, so see the first object, if it is not first body, if it is not fixed, so that means it will have 3 degrees of freedom. Okay, so this guy, the first body, if I consider, will have 3 degrees of freedom. Then each revolute joint will have 1 relative degree of freedom. So degree of freedom of this system is 8. The first body will have 3 degrees of freedom and the remaining will have 1 relative degrees of freedom. So that means I can have 8 independent motion. Okay, fine. Now, just to give you some more understanding, let us look at a 3D system. X, Y, Z. And I have a point P. Okay. Now, if I want to locate that point P, how many coordinates are required? So that is what is degrees of freedom. Can you please type it? Degree of freedom of a point in 3D space. Vasanta ma'am, if the first object is fixed, so then it will have 5 degrees of freedom. Because the first object does not move, all other joints will move. So that's why the drawings are very important. Based on the drawing, we should be able to answer. Okay. Now, what is the degree of freedom of a point in 3D space? 3. Okay. Yeah, it's fairly simple. We'll look at Px, Py, Pz or R, theta and H cylindrical coordinate system, or spherical coordinate system also has 3. R phi theta or R phi psi, depending on the convention. Okay, so 3 is the correct answer. So I will require 3 coordinates like that. Okay, now I would like to administer one simple quiz again. Simple, don't worry. Okay, just give me 1 minute. Okay, simple questions for. Can you please mute, sir? Whoever is that. Okay, this is another quiz. Kindly take this quiz. The link has been sent in the chat. So obviously those who are there in the session and those who have understood will be able to attempt these questions. So please take it up. You have 3 minutes. Okay, one person has submitted. Two responses. Three. Four responses. Another 2 minutes. See, these are simple questions. I mean, if you know the answer, you will type. Otherwise, you don't. You just take a guess. Whatever is the easiest or best guess you take. We'll be discussing the answers very briefly. Another 1 minute. See, these are the fundamental topics. Sometimes we fail to teach in the classes because we are always busy covering the syllabus. We lose these. We just skip some of these, and later on the students don't understand what is degrees of freedom, right? So sometimes it's okay if we just take a couple of classes like this because it becomes interesting to them. Okay, we have 10 responses, 12, another 30 seconds. Twelve responses. Again, the number of people attending this session is 64 here live, right? And I guess 1/4 are online. The last 20 seconds. Okay, I think I'll stop taking responses now. Fine. So let us review. There are few who maybe one person couldn't even get any correct answer. There are at least two who have got all correct. So let us look at the questions and the answer. What is the degree of freedom of a rigid body in 3D space? Right? So answer is, okay, so let us look at the question number 1. Okay, what is the first question? This one. How many parameters are required to represent a point in 2D space? So we have done this. So we require 2 independent parameters, px, py, or r and theta, any combination. So out of 16, 12 have got that correct. So that is a good thing. What is the degree of freedom of a point in 2D? Again, it is the same question. So parameters is nothing but number of independent, degree of freedom is nothing but number of independent parameters. Question number 1 and 2 are actually same, but put in a different manner. So obviously 12 corrected here. This 3 made mistake in the next question. What is the degree of freedom of a point in 3D space? So this is the topic we just covered last. So we need 3 parameters, px, py, and pz. What is the degree of freedom of a rigid body in 2D space? Okay, how come not everyone answered here? Okay, fine. So 16 have answered, 8 have answered correctly, which is 3. So we have translation along x, translation along y, and rotation about z, 3 degrees of freedom. Okay, this is an outside syllabus, right? Out of topic, because I hadn't covered it. That was the next topic to be covered, but I still wanted to see how you can extrapolate. So degree of freedom of a rigid body in 3D space. So 6 have given correct answer, 6 have given wrong answer. That's, I mean, different answer. But degree of freedom is 6. So let me give you an analogy in this. So if I have a rigid body in 3D space, I'm going to draw a cube. Okay, now obviously I can translate in this direction. I can translate in this direction. Similarly, I can translate in this direction. So 3 translation is fine. Now there are also 3 rotations possible. Okay, so let me demonstrate using this rigid body. So I can translate in the direction like this, in the direction like this, in the direction like this. 3 independent. Rotation, please observe, I'm rotating about an axis coming towards you and rotating about an axis, let's say horizontal axis, and I'm rotating about a vertical axis. Okay, so there are 3 degrees of freedom translation and 3 as rotation. So total is 6, 3 translation, 3 rotations, total is 6 stuff. So this is also another important thing that we have to deal with in robots. What is the degree of freedom of a robot? So that is one of the common question that we deal with. Okay, perfect. Now let me try to cover up the other topics slightly fast because we have to cover in next half an hour many things. So 2D translation, that means let's say I have a frame XY. Okay. And I have a frame, let's say UV, another coordinate frame. Earlier, these 2 frames were coinciding. Okay. I have one frame, I have another frame, they were coinciding, and I have moved one of them. So the motion that has happened is basically translation. I can translate in this direction. And similarly, I can translate in this direction. So what is the degree of freedom of this system? If I fix XY frame, UV frame is able to move. I can move this frame. So I can move it in two directions. I can translate along X, I can translate along Y. Okay. Now the same thing, I can say that I have put it on a rigid body. So there is a rigid body and I have attached a frame on top of that rigid body. So still we have XY. And this is U and V. So if I just do the translation of this rigid body, I'll require two parameters, that is translation along X, translation along Y. Okay. Now this information can be given using a vector. Let's say I'll call it as a D vector between, let's say, O and O prime or O1. Okay. Now D vector will have what? It's a two-dimensional vector. So obviously we'll start writing vectors in a column format. It will have dx and dy. Okay, so dx and dy are two parameters, independent parameters, right? So if I want to represent 2D translation, I can use this vector to represent that 2D translation. Okay, now, so there's something known as 2D rotation. Okay, now, so this is again very important topic. So I have, let's say, U and V frame, and I already had X and Y frame. So we did rotation of U and V frame itself. So earlier, both the frames were coinciding. Then we rotated one of the frame. Okay. Now there are certain ground rules which we'll consider. U and V are unit vectors. Okay. U and V are unit vectors. Unit vectors means it will have length as 1. Now, if I want to represent this system, I will require an angle, let's say theta here. Okay. So if I give you the value of theta, you will be able to draw this U and V vector straightforward. Okay. Now, this is okay for 2D case. But when we go to 3-dimensional case, the way the angles are specified, it becomes confusing because here there is only one angle. There will be 3 angles. What adder we rotate, about which axis we rotate. There are so many things that happens. Okay. So one of the easier way to represent rotation is using something known as what? What are we going to use? There's a topic known as direction cosine. Okay. So we deal with something known as direction cosine. That means we are going to represent these U and V vectors. Okay. So let me start trying to type or write. Now, u vector similar to the dx dy vector. See, we have not translated it. It is still at origin. So this is a vector, right? Now, if this is a right angle triangle, u vector can be written as ux and uy. X component of u, because it's a vector. A 2D vector will have two components, x component and a y component. Okay. Now, we assume that the length of this u is 1. You remember r cos theta, r sin theta form? So that was very important because that will come handy here. So ux is going to be 1 cos theta, which is nothing but cos theta. So I'll just write c theta, cos theta. And uy is going to be 1 sin theta. So that is going to be sin theta. Simple. OK. Now we have to write v, another vector. Now, obviously, this is where that assumption of measurement of angle from the positive x-axis is very important. So the angle till u is theta. So obviously from the x-axis, the angle till v will be theta plus 90 degrees or 90 degrees plus theta. OK, so the v vector, which is vx and vy, will then become, please bear with me, I have to write slowly. So this is again going to be r cos and r sin form. OK, so the only thing is it is going to have 1 into cos of 90 plus theta. So that is the angle measured with respect to the positive x-axis. Please remember, when we deal with such system, so you don't have to worry about where the angle is given, right? So this angle is also theta. So I can always say I want to measure with respect to this. But simplest is measure all the angles with respect to positive x-axis, and you don't have to worry about the sign. Why? So if you remember this ASTC form, so this ASTC form takes care of this positive and negative sign of the value depending on the value of theta. OK, similarly, I'll have 1 sin theta. (90 plus theta). OK, so this is going to be cos of 90 plus theta is minus sin theta. OK, and sine of 90 plus theta is cos theta. So the direction cosine is basically represented as, let's say, rotation matrix R, which corresponds to ux, uy as first column, then vx, vy as second column. See, we are just building upon what we already know. It's just representing in a different form. So that's why these topics are generic. Anyone who has passed 12th, they should be able to understand what we are talking. Okay. Now this R, I can write it like this. Cos theta, sin theta in the first column. In the second column, minus sin theta and cos theta. Okay. So rotation, when we do rotation of a frame with respect to another, so we just need one angle because that is what is one relative degree of freedom, theta. But to have it useful in certain applications, like in the next slide, I'll be clarifying. We represent this rotation in the form of direction cosines. That means components of the u vector and components of v vector arranged in a 2x2 matrix. So that is what we have written, R. Okay, now obviously if I have a frame, it can translate and also it can rotate. Okay, now when we have such things, then we need both information to be put in one matrix. So that we call it as HTM. HTM stands for homogeneous transformation matrix. So let us look at this particular scenario. So I have an XY frame which is fixed, and I have an UV frame which is like this, rotated. Okay, so we can represent the translation using a D vector. There's nothing wrong in that. D. And this angle, we'll call it as theta. Angle with respect to positive x-axis. So I have drawn one parallel line and then we have measured angle with respect to that. So again, degrees of freedom of this moving frame is 3 now, because translation will have 2 degrees of freedom, rotation will have 1 degree of freedom. Okay. Now, however, if we want to represent this as a homogeneous transformation matrix, it will have a rotation part, which is a 2x2. Rotation matrix is what we did in the previous slide. Then it will have D vector, which is 2x1. Then, so homogeneous means we have done some manipulation. Okay, manipulation in the sense to include both translation and rotation. We did some jugglery, and due to that jugglery, we'll have some extra row. This is a 2D system, but still we'll have 3 rows. Okay, so the last row will look like this. The last row will have 0, 0, 1. This is 0, this is 0, and there is a 1. Okay, so this one, let me try to write it in a different manner. So R was basically cos theta, sin theta, and minus sin theta, cos theta, then This is dx dy. See, these equations are fundamental. I mean, in robotics and computer graphics and CAD, we have to deal with all these equations. Sorry, 0, 0, 1. Okay, so this is what is a homogeneous transformation, which represents both translations. So dx dy correspond to translation, theta corresponds to rotation. So when we put together, we have to add one additional row, which corresponds to 0, 0, 1. Okay, so similarly, we have 3D translation, rotation, homogeneous transformation, and all other things, which I'll be demonstrating right now. Okay, so let me open up a browser. I'll go to a website called RoboAnalyzer. So RoboAnalyzer is a product developed at IIT Delhi, and I was pursuing my master's there in 2009. So it's almost 14-15-year-old product, and it has undergone a lot of revisions, and still we have been adding new stuffs. And in this, we have something known as WebHTM, a homogeneous transformation matrix, HTM, right? Now, this corresponds to two 3D coordinate system. The bigger one is, let's say, XYZ. Then there's a smaller one, which is UVW. Okay. Now, to understand whatever we have done so far, let me just go to side view, also the top view. You can see that both the frames are coinciding. Now, if I give dx as 4 and dy as 3, and if we click on translate, you can see that it moved. So this is pure translation. I was able to translate the frame, the UVW frame. See, this is, let me call it as 2D, because again, later we'll go to 3D, but this view is nothing but 2D. Okay. Now, somewhere here, we also have reset. Reset means it goes back to the earlier system. So if we want to rotate, we'll rotate about Z axis by, let's say, 30 degrees. If I rotate, the frame rotated. You can observe here. I've given theta, and accordingly it moved, right? Fine. So we have covered pure translation, pure rotation. We can also do combined. After translating, I can rotate. Okay. So this is what happens. I can keep rotating. So if you have observed your PowerPoint slides, right? Sometimes something keeps bouncing. There's a rotation that happens, or when you look at movie marriage video or something, some animation keep happening, right? So in all those animations, these underlying graphics or transformations are used. Without whatever we have covered so far, none of the animated movies can be produced. Okay. Now this is for two-dimensional case where we are able to understand something on HTM. Okay, let me go back. I'll very quickly explain 3D translation. So if I have UVW frame, XYZ frame, so D vector is given by dx dy dz. Okay, dx dy dz. Okay, I need to hurry up because in next 15 minutes I have to stop. So there is UVW frame. There's XYZ frame, I can translate. So when I do translate, there's no rotation. Okay. Similarly, if I do 3D rotation, so if I have U, V, W, right? Now the rotation matrix, let's say I use Q or letter R, is given by, it's similar to the 2D diamond stuff. So we assume U, V, W as unit vectors. Length is 1. Okay. So that means this will have X component, UX, UI, and UZ. So this is the first column. Similarly, it will have Vx, Vy, Vz. These are the components of a vector. Components of the vector means I'll explain in that software. Similarly, Wx, Wy, Wz. I hope you are all writing it down because these are the stuffs we'll be using again in the next slide. Okay. Now, obviously, there are 9 elements here. These 9 elements can't be random. I can't have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Sorry, because if you remember X, Y, R, theta, there was some constraint. So there are 3 rotations. So that means there should be 6 constraint equations what we have. So what are the constraint equations? If I have this as moving frame, the angle between U and V is 90. So that means U vector dot V vector dot product between them is 0. Similarly, V and W dot product is 0. W and U dot product is 0. Dot product is a vector operation. Getting a shadow, one shadow or the other, projection. Okay. So when these move, there are 3 constant equations which derive or which are basically given for 90 degrees. So I can't have random UVW values. It has to match something. The other 3 constant equations are the length of U, V and W are always going to be 1. Okay. So that means if I use U dot U, dot product of U on itself, I should get 1 because it is projecting completely on itself. Similarly, V dot V is 1, W dot W is also 1. Okay. So that means out of these 9 values, we can only have 3 independent and remaining 6 have to be dependent. So that is what is the meaning. Okay. Now 3D HTM. So that means if I want to write information of translation and rotation together, so I'll have to write it in a 4x4 matrix. Right? You remember translation was in the last column. So I can write translation here. Dx, dy, and dz. And after dz, so we'll have 1. So that's kind of, let's say, thumb rule for you. You don't have to worry why it is 1. Similarly, so the last row will have, remember it is a 4x4 matrix. So 1 column is already taken. So we'll have 3 more columns. So 0, 0, 0. So this one. Okay, so UX, UI, UZ, all these things will come here. It's a Q matrix, which was 3 cross 3 from the previous slide. Ux, Uy, Vz, Vx, Vy, Vz, Wx, Wy, Wz. So all these information can be put in one matrix, and we call that as homogeneous transformation matrix. Now, please allow me to demonstrate all these things in this HTM module in our RoboAnalyzer software. By default, it is 3D. What you see here is user control. Don't worry too much about local and global for now. Later we'll understand. We have something known as translation and rotation. We have seen translation, rotation. What you see here is the homogeneous transformation matrix, the 4 cross 4 matrix. Okay. Ux, Uy, Uz, the ones that are in red color. Vx, Vy, Vz, Wx, Wy, Wz. Red, green, blue. Red, green, blue. Typically in graphics and CAD, we use RGB. Even for pixels also we use RGB corresponding to XYZ. Then the black last column is basically DX, DY, DZ, the translation part. Okay, let me just very quickly demonstrate what I'm going to do. I'm going to translate along x-axis. So when it translated along x-axis, you please observe this HTM. Other than addition of decimal values, nothing changed in the rotation part because it did not rotate. It is just translating. This is now 4 from here till here because we moved along x-axis by 4 units. Other two are still remaining 0. Now let me try to translate along y. So along green direction it moved. You can see here. It moved along the green direction. So the dx, dy value changed. Now it is 4, 5. Similarly, I can just do translation along z direction. Let me just translate. So we translated along z direction, which looks like this. It has moved up. Earlier it was in xy plane. So now the effective transformation is it has not gone on any rotation. However, translation it has undergone 4, 5, and 6. OK, I'll reset. So we have understood what is translation. Now let's try to understand what is rotation. See about Z axis. If I rotate by 45 degrees, what will happen is, so you saw a rotation happening and the projection of this Ux, Uy, Uz. OK. OK, now this is U vector. The components of U vector is its shadow along x-axis. So this is x-axis. If I cast a shadow, this much will be Ux. It is given by R cos theta, cos 45. Similarly, along y-axis, the shadow, if I put a light from here, it will be this much. This is R sin theta. Sorry, R sin theta. So R cos theta is cos 45 here is root 1 by root 2. This is the value. Sin theta. Then the last row will be 0 in this case. Cos theta, sin theta 0. Now this one is 90 plus 45. That is 135. OK. Cos 135 is Vx. If you remember, cos is negative in the second quadrant. Right. So that is why. Sorry. What did I do? Sorry, I forgot. We still consider 45 because we have already done that part. So this is minus sin theta. If you remember in this slide, it is there. This one. Minus sin theta, then cos theta. So minus of sin 45 plus cos 45, 0. Then the blue one is undisturbed. So that means these two axes are parallel. So that is why z-axis or w-axis is parallel to z-axis. So that is why it is 0, 0, 1. Okay. So by performing these motions, we were able to generate the homogeneous transformation matrix because it corresponds to the independent motions that we have done. So similarly, you can play around with different motions that are possible along this. So for example, rotation about x-axis. If I rotate by 90 degrees, you see it rotated and the corresponding HTM changed. Rotation about y-axis. Again, it rotated and the corresponding HTM changed. Okay. So this particular interface is available for free on RoboAnalyzer website. And you have to go to web HTM, homogeneous transformation matrix. And since we are on this website, let me try to very briefly explain what is this software. So we have developed a set of video tutorials, those who want to teach such topics. So please go through these video lectures link. There are a lot of small videos. So basically, we had one FDP in IIT Delhi, faculty development program. So during that time, we recorded all these videos and we cut them and we have put it on YouTube. Okay. So basically, we have covered till here, more or less, in the first, whatever, 1.5 hours I had. Later on, you can go through these videos and also try to extend further. There are more videos. And towards the bottom of the page, we conducted something known as RoboAnalyzer based online competition. Again, during COVID, we wanted to engage our students in some useful manner. So we created few video tutorials. We conducted some competition. And these video tutorials help in self-learning, similar to any NPTEL course. Okay. So fundamental forward and inverse kinematics of 2R, 3R planar manipulator. And most importantly, we have used, let's say, a simple MATLAB program, okay, to perform this forward kinematics and also do the motion animation, right? So for example, you want a robot to draw a circle, you want a robot to draw a line. So what is the mathematical code required for that? So those have been covered. So people who are interested to learn programming, this is a very good starting place. Basically, I have typed as and when it was getting recorded. So it's very important to go through such material because ready-made material, if you get, you don't know what kind of mistakes can happen. So even one of the videos, so for example, this particular video, it says more than 1 hour. So somewhere I had made one small typo and it was not easily detected. So there's some debugging skills that people can learn from this video. How to debug if there's a mistake. Okay. So this is about the homogeneous transformation matrix, and the software is also available called as RoboAnalyzer. Let me try to very briefly demonstrate what it is. I have an older version which was free, but now it has become commercialized. So if someone needs RoboAnalyzer, there is a partner in Pune, SVR Infotech. So they will be able to give trial license and later on actual license. Okay. Very quickly, in 3 minutes, I'm going to demonstrate this software. So this is a simple 2R robot, 2R manipulator, and certain geometric information we can enter, which are known as DH parameters, Denevitt-Hartenberg parameters, which basically determine the architecture of this robot. Then we can click on this FKIN, forward kinematics, and we can observe some motion. You see the 3D model. This is a 3D model, right? Like a CAD software. So we developed this using OpenGL, Open Graphics Library, the 3D graphics. But the geometry and other things were developed by me. Okay. And that is the reason why some of the topics which we discussed today are very clear, because when you start doing your own product, you have better clarity. So that is what is the meaning. Okay, so we can do some motion of this robot. And if you observe, by changing one particular value as from 0 to 90, I can change the shape of the robot. Earlier, both the joint axes were parallel. Now it has become skew. Now let's observe. So it is no more parallel. Earlier it was like this. Now this is like this, the next joint axis. Okay. So for people who teach Robokinematics, so we have this topic called DH parameters, Dynamit-Hartenberg parameters. Again, one can refer to these videos to understand what are those DH parameters and how RoboAnalyzer can be used in a course. Okay. So similarly, we have plots. If I want to look at the end effector point, how the x-axis, x coordinate is moving. Similarly, how the y coordinate is moving, and similarly how the z coordinate is moving, right? These are important if you are doing a course in robotics and where you ask the students to develop some MATLAB program. Once they have the results, they have to validate, right? So this software can be used to check whether their solutions are correct or not. So we have been doing such activities. Okay, so this is about forward kinematics. Means I know the value of theta. I should know where the tip has reached. That is forward kinematics. So inverse kinematics means if I know the tip state, position of the tip, what joint angles should I give such that I reach there? Okay. So in inverse kinematics, let's say I've taken 2R planar, same robot, and link lengths I've given. And we want to reach a particular end effector point. So please remember, in inverse kinematics, multiple solutions are possible. So that means if you observe, I'll go to top view. So if you observe, I wanted to reach this particular point, and the joint angles required to go there are given here. Or I can choose other solution. So you see, I can flip to reach the same point. I can reach in one like this, another by basically going in another direction. Okay. So two solutions are possible for a simple 2R manipulator, and depending on the situation, you can choose what you want. So this is about inverse kinematics. There are a lot of robots that are available. You can, in fact, look at a CAD model of a robot. For example, there is a KUKA robot. So let me go to isometric. This is a CAD model of a robot. So I've given the robot to reach a particular, configuration. Now in the inverse kinematics, I can choose which solution I want to go. So multiple solutions are possible. As you can see, robot is changing its joint angles to still reach the same point and same orientation. We call the orientation of the end effector. Okay, so all the mathematics have been, let's say, derived, and then we have implemented all these in a C# application. Visual C# is used, and for graphics we have used OpenGL. So this work, it has basically took almost 4-5 years for completion, and later on small modules we have been adding. Okay, so finally I'll be demonstrating something known as virtual robots. Virtual robots means, let me say, we can use CAD model of a robot, and there are some joint jogging. So for example, you want to see how a robot moves. So this is more like a, okay, so this first joint is more like our waist. Okay, we are rotating about the vertical axis. The second is more like our shoulder. Okay, then the third one is more like our elbow, like this elbow. Then the last three joints, we'll call them as wrist. You can see the gray color guy moving here and there. Similarly, there's a cyan color rotating, and finally the red color flange is there. So that is also moving. Here you can see if I rotate this, it moves, red moves here and there, rotation. So there are 6 sliders. Okay, so that means there are 6 joints. So what is the degree of freedom of this system? It is 6 degrees of freedom because I am able to control 6 motors independently, right? So degree of freedom of this robot, if someone asks you, is 6. Similarly, we can do something known as Cartesian jogging. I can take the robot along straight lines. You can see I'm trying to draw straight lines. The tip. See again, the math and other things, it is possible to understand only if you understand the starting part of my lecture. Similarly, you can see there is a rotation that is possible. The tip is not moving now. I'm only changing the orientation of the tip. Okay. And when we do all this, you observe that the homogeneous transformation on the right side is changing. So that means the position and orientation of the tip with respect to the base is changing in this table. That is what is homogeneous transformation. Okay. Yeah, I think I'll respect the time. It's 3:50. I would like to formally close this session with last few slides. These slides I'll share with organizers. They will probably share it to all of you. So my supervisor is Professor S.K. Saha, Subir Saha from IIT Delhi. So he has written a textbook on robotics. So basically, the first edition when it was written, I had just joined. It was very difficult to just understand from textbooks. So since I had some experience in the programming and graphics, so together we came up with this software. Okay. And in the next version, we have used a lot of RoboAnalyzer analogy inside the textbook. Okay, so I guess these are the contact details. If at all you need any assistance, you may please reach out to us in one of these mail IDs. Saha sir would also answer, but again, he wouldn't understand the context. You may please email if you have any concerns, and you can cite this FDP and I'll be able to get back. So with that, I would like to formally close my session. Thank you, organizers. Thank you, audience.
Thank you, sir. Thank you for your wonderful session. Really, it's a very useful session for both mechanical as well as ECE people.
Yes, thank you.
Sir. Sir, how can the participants then contact?
Yeah, so they can email me, and I mean, there is something known as on the RoboAnalyzer website, there's a contact form, but definitely they can email me. I'll send the amritha.edu. So if they have any doubt on how to prepare for such courses or how to use RoboAnalyzer software, I'll be able to help.
Okay.
I mean, this topic is very broad. We can't cover Robokinematics in 2 hours. It's just that the starting part of this session was more on the fundamentals, and the later part was on how those fundamentals were used in the application.
Yes, sir. So actually that course basically covers right from basic parts till the advanced,
Yes, sir.
part. Right. Okay.
Any questions from the participants? Any questions?
Yeah, you may please type. I will be able to answer.
Dear participants, audio is also enabled for all. You can ask directly. You can make on your mic and then you can ask your doubts.
Any doubt, any tips, any clarification? Okay, I have my email ID. If there is anything, you may please contact.
Okay, thank you very much, sir.
Thank
Rajeev,
you.
sir.
Thank you all.
Okay, the participants can share. We already shared the feedback link. Please submit the feedback link. If you have any assistance or any help from the Rajiv sir, sir already shared sir's mail ID. So please go through that. Thank you very much, sir.
Okay, sir. If there's nothing else, then I'll. Okay, it didn't really want to learn today was subject. Yes, correct, madam. Now, it is a very difficult topic. So those who are interested may please go through the video to lectures on the RoboAnalyzer website. I mean, whenever we got time, we recorded videos, and hopefully we'll be doing some more in the next couple of years. But otherwise, you can, I mean, go through the software also. Okay, sir. If there's nothing else, then I would like to log off.
Okay, thank you.
Thank you. Thank you all.
Thank you, sir.